Hello everyone. At this moment when I am recording this lecture, the final test of Anderson Tendulkar Trophy between India and England is going on at Oval, London. England is batting, India is fielding, the final inning is going on, terrific contest, but I have a very simple question to ask you. Suppose this is the cricket ground at Oval and these are the batting stumps. The question is, which fielder will see these stumps very clearly? Those who do not understand cricket may assume that these stumps are nothing but three sticks standing on the ground. Who will see these stumps very clearly? An obvious answer is, very simple answer is, the wicketkeeper. And wicketkeeper for this match is Dhruv Jurel. So Dhruv Jurel will be standing somewhere here. So he will see these stumps clearly, whereas a fielder who is standing around point region may not see all these three stumps at all. So maybe let us see the view of wicketkeeper and then the view of someone who is standing around the point region. Most likely it is our great fielder Ravindra Jadeja. Okay, so from wicketkeeper these stumps will look like this, right? Very clear, maximum gap as possible between any two stumps. Okay, whereas if you see a fielder who is standing somewhere near the point region, maybe the stumps looks like this, maybe the stumps look like this. Okay, so you see that here the gap between any two stumps is not much. By the way, these are the same stumps, the only thing that differ is from where we are looking at these stumps, along which line we are looking at these stumps. Okay, so this is view of our great fielder Ravindra Jadeja. Okay, so Ravindra Jadeja, okay, and Dhruv Jurel here, Dhruv Jurel. Okay, great. But why we are talking about these views? In this lecture we will discuss one of the very famous, fundamental and very interesting AIML technique. The technique is called principal component analysis, and one of the main motivation of this technique is to find the directions along which, if we see the data, we see the data very clearly, like how Dhruv Jurel is seeing the stumps. Okay, so now let me take you to a different scenario. I have this piece of paper. Okay, I will draw some points on it. Okay, so let me draw some points on it. Okay, I hope you are able to see these points. Okay, now for the time being, forget about this piece of paper. So these points right now are floating in this recording room, in this 3D space. So every point can be represented by three coordinates, x, y, z. Okay, so you can assume this to be length of this room, breadth of this room and height of this room. So every point can be uniquely represented by these coordinates or these features, whatever name you say. Okay, but now come back to this piece of paper again. You know that these points are on this plane, the plane of this page. So fundamentally you can also represent the same point by just two coordinates. You can assume this to be x-axis, you can assume this to be y-axis. So every point can be uniquely determined by just two coordinates. You can call this x and y. So x, y coordinates. So I mean, what is happening? The same point earlier were representing by three coordinates. Now we can represent the same point with two coordinates without loss of any information, right? The second motivation of principal component is to reduce the dimensions of these data points. Remember, the earlier the dimension was three coordinates. Now the dimension is 2. Okay, so the scenario is like this. Earlier these points were represented in 3D space. Okay, so let me draw these points. So I will draw a few more points than what I draw in our page. Okay, so let me draw more points here, and each of these points has now 3 coordinates. So let me write these axes as x axis, y axis and z axis, and every point, for example this point will have now 3 coordinates. Okay, here 3 coordinates here. The same points we then represented in our 2D plane. Okay, 2D plane. So let me draw the same points. So maybe I will do the justice here. Okay, my drawing is not so good, but I hope you will get what I wish to convey here. Very good, very good. So now, so suppose now the axes are this x new, sorry about this x new. So these are new axes and y new. So now only there are 2 axes. So every point will be having now only 2 coordinates. Okay, so the same points now we are representing with only 2 coordinates. In fact, as we go along, we will see there is a better way to represent these points such that we visualize these points clearly. Okay, what we mean by clear here, if you see this, if you see here, so let me actually give you some intuition, and maybe I will draw the same points again here. So the points were like this, right? Points were like, let me put few more here. So if you see that, if I have drawn the axis like this, so suppose this, right? So let me write now this as x new 2, let me write it as 1, y new 2, now let me write it as y new 1, and now if you see, if I visualize these points along x new 2, I will see the data better way. So what we mean by visualization, we will see that this is done through projection. So if you project earlier all these points on your x axis one, the projection were like from here to here, right, for all these points. So this much was the projection or spread of data, whatever you say. So right now I am saying very informally, but now here if you see, this will be your projection to, I mean project, when we project all the points. So this will be the spread, in fact this will be the spread. So this spread is more than x new 1, right. So this axis, if you watch these data points along this new axis, you will watch these points better way than x new 1. And of course you will ask then, oh okay, so we are losing the visualization along y new axis, but our aim was to find some direction along which we can see the data very clearly. So we have actually got x new 1. So this will be our main directions along which if you watch the data, we will see it very clearly. PCA actually finds such directions. Okay, so in short, there are 2 aims. So first is to find the directions, in fact good directions, such that the data visualization is very good. Find good directions or axes, we will see that these are nothing but axes, directions such that the data visualization is very good. The data visualization is very good. Right now I am saying this very informally. We will mathematically see what we mean by this. And the second aim is this, to present or to represent the data in lower dimensions, basically less number of features, in terms of less number of features, such that most of the information is written, such that the most of the information is retained. Okay. So basically the aim is to reduce the size of data such that the maximum amount of information is still retained. Okay, and we want to visualize this data very clearly also. Now, before we move ahead with the basic mathematics or basic logic behind the working of principal component analysis, I have a disclaimer to make. I am not an AI/ML expert. I have never ever done any AI/ML related coursework, and I have never utilized any AI/ML technique for my research. But still I am doing this show off of teaching PCA. Why so? Being a faculty in the Department of Computer Science and Engineering, I often come across many students who are interested in AI/ML, and some of them have actually done research on it. But when we ask some working of AI/ML tools or techniques, most of them are null and void. This is kind of unfortunate. It seems that some rat race is going on, but the problem with rat race is what? Even if you win, you are still a rat. This is the famous quote by Lily Tomlin. Okay. So, purpose of this show off of teaching principal component analysis to you is to make you realize that it is not difficult to understand the working of any AI/ML technique. All you required is some basic mathematics, sometime basic linear algebra, sometime basic probability, sometime basic calculus, and that's all. And I promise you that once you understand the basic mathematics or basic logic behind those techniques, you will enjoy your research, you will enjoy AI/ML a lot. Okay, so let us start the journey. First, we will see that what we mean by visualizing or projecting a point or data along some lines or vector. Okay, so let us take first of all a 2D plane. Okay, so this is your x-axis, this is our x-axis, and this is the y-axis. Remember, all these axes are actually made up of vectors. Which vectors? Okay, so there will be some vector here, right, what we call 1 0, right, and there will be a vector, unit vector here, this will be 0 1. Your x-axis is nothing but scaling of 1 0. You keep on scaling the 1 0 vector, you will be getting x-axis, and similarly you scale 0 1, you will be getting y-axis infinitely, right. Now, suppose I pick a point in this 2D plane, point or a vector. Suppose this is your vector v or a point, whatever name you suggest. So, it will have two coordinates, right. What will be those coordinates? How will you find those coordinates? Let us go back to our school days. So, how we were finding it? We were actually, so this is our vector, right, and I want to know what will be its coordinates, these two coordinates, right. So, what will be these two coordinates? We were projecting this vector or point along x-axis and then y-axis. Projection is this. Okay. So, earlier we used to call it perpendicular or what in that language, but this is, we will call that, we will put an orthogonal vector to x-axis and similarly orthogonal vector to y-axis. Okay, and wherever it will cut here, this will be your projection along x, and similarly this will be the projection along y. So, the length of this part, basically this part here, from here to here, similarly from here to here. Okay, very good. In the same way, we can actually project v along some other direction also, some other direction. So, let me take some other direction. So, let me take this edge u. Okay. So, how we project this? We will do the same thing. So, we will actually put an orthogonal vector here, this, right, and so this part will be basically this. So, let me do it with the red. So, this part will be the projection of v along u, and that is how actually we measure. So, we can also say that, oh, when we observe v along u, we will see this part, we will see this part, right. Okay. Now, let us see the higher dimension case. I mean, everything is pretty much similar. So, here your data points were 2 dimensional, there were 2 coordinates. So, now in higher dimension there can be many coordinates, right. So, suppose now you take about the high dimension, right? So high dimensions. Okay, let us take two vectors, the same vectors v and u, but now in high dimension. Basically means that now we will have many coordinates, right? So let me call these coordinates as v1, v2 up to vd. Similarly, u will also have d coordinates. Okay, so this u1, u2, ud. So now these points are in your d dimensional space. Remember earlier they were in 2-dimensional space, now d equal to 2. Okay, so now what we mean by projecting v on u? It's the same thing like we did in 2D case. So we will put a projection here. Okay, so this will hit somewhere here. So this part will be nothing but some scaling of u. So this will be nothing but alpha times u. So this will be a factor. So we want to now find what will be alpha, what will be this scalar quantity, what will be that scaling factor alpha. We know that this vector, what will be this vector, by the way? This will be nothing but v minus alpha u, right? This vector from here to here. Okay, very simple school stuff, right? So now this part, this vector is orthogonal to u, right? So basically we know that if two vectors are orthogonal, their dot product is 0. So u transpose v minus alpha u is equals to 0. We know that the very basic mathematics stuff, which implies that u transpose v minus alpha u transpose u equals to 0. That means alpha equals to u transpose v and u transpose u. So what will be alpha u? What will be this vector? What will be this vector? So this is nothing but u transpose v, u transpose u times u. So we can very safely write it as this, the dot product of u and v, and then this vector. This vector is nothing but, this part is nothing but unit vector, right? This is unit vector. You are dividing a vector by its magnitude. So unit vector along u, along u. In fact, if I had taken u to be the unit vector, then alpha was nothing but this, right? Simply u transpose v. Very good. If you see it carefully, it doesn't matter how long u is or how short u is, your projection will always be this one, always be this one. So alpha is the crucial quantity here. So please keep this in mind. We will be using this a lot in this lecture. Okay, very good. Okay, now suppose we have n data points in d dimensional space. So suppose these points are x1, x2 and up to xn, and every point has d features or d coordinates. So they are lying in d dimensional space. Okay, what we mean by projecting these points along some line u or some vector u? Remember, when we are projecting a point on some line like u, we have just said that the length doesn't matter. So I will take u to be a unit vector. So suppose u is a unit vector, u is an unit vector. Okay, so now I have to project all these points along u or measure all these points along u. So the process is same, like we have measured recently v on u or projected v on u. In the same way, we will now project every point x1, x2 up to xn on u. So how we can actually write it in very concise form? So actually what I can do is, I can, so this will be nothing but, so when you project x1 on u, so what will be the quantity, what will be the alpha? Alpha will be nothing but u transpose x1, right? Similarly, when you project x2 on u, it will be nothing but u transpose x2 and so on. This will be nothing but u transpose xn. And by the way, this we can beautifully write in terms of matrix also. Suppose your data matrix is this. Basically in data matrix, so you are putting these vectors or data points x1 up to xn So these are actually, I am writing it as a column. So these are points in your d-dimensional space, and you are projecting these points along U. So you can actually simply multiply this by U transpose. So this you can, this matrix is nothing but U. So I can actually, this matrix is nothing but X. So I can actually safely write. So this is data matrix, okay. And when you project all these points, okay, on U, so this will be nothing but U transpose X. Very good. What will be the size of this matrix? This matrix X, this will be nothing but D cross N, because there are D features and there are N points. Okay, so this will be your projected vector. So there will be basically N entries, but these entries are coming after projecting every data point on U. So there are N data points, so there will be N projections. Okay, so very, very good. Pictorially we can see this. So basically there is a line here which is unit vector U. There are different points x1, x2, maybe x3 and up to xn. We are projecting every point along this vector U. I am considering this as a unit vector. Okay, and then this, I want to know these projected points, how far they are relative to each other. Like we were curious about how far these terms are along different lines. So I want to know along U how far these points are relative to each other, and this is beautifully captured by variance. Okay, so now let us see two very basic quantities, those we know since our school times, the mean and variance of data. Okay, so and in particular the variance tells us how far our data is from its mean. Okay, on an average how far our data is from its mean. Okay, so let us take an example of number line. Okay, and let me put some points on it. Okay, so suppose these are first some points. Okay, so let me call it set S1, and then also I take these 3 points here and let me call this set as S2. Okay, now I ask you a very simple question. Okay, in this set the data is more spread, of course in S2, right, because the gap between, on an average the gap between any 2 points is large, whereas in S1 the gap is very small. Okay, so we see that S1 has less variance. Okay, so less variance, and we will shortly calculate how we actually calculate this quantity. Okay, more variance, and we need actually more variance to visualize our data very clearly, right. So we can distinguish among the data when the variance is very high, and our PCA does this very beautifully. Okay, very good. So now let us formally define what we mean by mean and also what we mean by variance. Okay, so suppose we have n numbers here. Okay, so n numbers x1, x2 up to xn. Okay, dot xn. Remember earlier I have represented the vectors by these numbers x1, x2, xn. Right now I am just representing these numbers. So you can assume that numbers are also 1D vectors, right, where there are just one component. Okay, so the mean of these numbers is nothing but we will represent by x bar. We will add these numbers, okay, and then divided by n. Okay, and how we calculate the variance? Okay, how we calculate it? Let us recall our school days. We will subtract from each number its first of all mean. Okay, so I will subtract mean from x1, then I will subtract mean from x2. Okay, and then from and dot everywhere xn minus x bar. Okay, and then I will take square of these differences. Why we take square? Because these differences could be negative also, right, and we want how spread these are data, so it will make positive, and then we add all these gaps, square of gaps. Okay, and then we divided by n. So this is variance, very simple. Okay, but I will actually write this mean and variance in some different terms, in fact some product terms of product of vectors, because this will make our life easier. We will see it very shortly. Okay, so let me actually denote these numbers by a vector. So suppose x is your row vector, basically a kind of a line where I am arranging this number x1, x2 up to xn. So this is a row vector. I hope you know row vector and column vector. And suppose one is my special vector. Let me mark it by more darker or more bolder here, and suppose this is all one vector. Okay, very good. So it has also suppose n entries. Okay, so this is all one column vector. Earlier so this was row vector, this is column vector. Okay, very good, very good. Now how can I write x bar? X bar I can actually write by just this product of these numbers, right, x and 1. So what will be this quantity? So this is nothing but this is summing every entry of x basically, and then this sum divided by n. So let me actually write it. So this is nothing but x1, x2, x2, xn, and then of course we are making this product, okay, n. So basically, so x1 plus x2 and xn and so on, and then we are dividing it this whole quantity by n. Very, very simple, very, very simple. Now similarly I will write the variance. Okay, so variance of x. So variance of x is nothing but, so from first of all from each entry I will subtract the mean, right. So basically what I will do, so this is my vector x, right, row vector x, and from each entry of it I have to subtract the mean. Okay, but now this is vector but this is quantity. So what I have to do, I have to multiply this mean by all one vector, but now right now I have to do transpose because this is row vector, right, and then I have to actually square these entries. Okay, how can I do this? By using matrix multiplication or row or vector multiplication. So what I will do is this, because this is row, okay, and then I have to multiply with itself so that the squaring terms are there, right. So basically then I have to take multiply of this with same quantity but now in transpose, right. So I will take transpose of it, okay, and then divide this whole quantity by n. Okay, so now let me make use of the same line divided by n. So very, very nicely. So I have now written the same quantity. You just have just bunch of some number, calculate mean, calculate variance, and then write also in terms of as this representation. So it's very, very easy to just verify, right. Okay, so now we will make use of this for our calculations also. Remember, I have to find the variance of numbers after when I am projecting my data points along some line. Okay, so I have, remember I have put just now just for maybe 5 minutes back I have put, so suppose there were points x1, x2 up to xn in very, very high dimension, suppose d dimension, and suppose they are projected on some line. So suppose this is unit vector u. So projection means this, okay, like this. So I have to find variance of this. The line along with this variance will be very, very high. I want to find that line, I want to find that u. That u will be my first principal component. Okay, very good. Okay, so for now next 4 or 5 minutes I want some patience from you. I want to calculate variance of the data points after projecting on some line or some vector u. Remember, our data points are now in d dimensional space. I want to project all these data points along some unit vector u. Now I want to find what will be the variance after the projection, and we will see that solving this projection or solving this variance of projections, we will get a very, very beautiful and famous matrix that we call covariance matrix. So let us start. Okay, so these are suppose n points in d dimensional space, and let me write this in the matrix form. Okay, so I will make a matrix or data matrix of these points. So this is point number 1, this is point number 2, and so on. Okay, very good. So there are n points and every point has d features. So this matrix will be d cross n, and we know that once we project these points along some unit vector u, so let me write as unit vector. Okay, so what will be these projections? So these projections are nothing but, so this will be nothing but u transpose x1, this will be nothing but u transpose x2, this will be nothing but u transpose xn. So I can actually write this as in very, very shorthand. So this will be nothing but u transpose x. So basically this will be a vector, this will be a row vector in which there will be n point, but now these points are the projected point once we project all these d dimensional data points along some unit vector u. Okay, and I want to find the variance. Okay, so variance of this vector. So variance of this vector, in fact variance of these projections. Okay, so this is nothing but we will utilize the formula just we have seen. Okay, so this is nothing but this. So let me write. So from each entry of this this vector u transpose x, I will subtract its mean first of all, mean. So let me write its mean is this. Okay, and then of course because I have to subtract from each entry this, and then I will take transpose of the same vector. So you just see what I have done in one dimensional case in just 3-4 minutes back. Okay, very good. So same thing. So by the way, this is also one dimensional because these are the points, right? Okay, very good. So now very good, the same thing, u transpose x, mean x 1 transpose, and then transpose of this, and then we will divide it by n. Okay, so have some patience, let me solve it. Okay, so this will be equal to, very good, 1 by n, and then because there are n points, right, 1 transpose x. So let me open it. So how, so this is mean. So how we calculate mean? So mean of this vector is nothing but this, I will multiply with 1 divided by n, 1 transpose, and the same thing. Very good, very good. So u transpose x, yes, 1 divided by n, 1 transpose, and the same thing. Okay, now let me take this transpose inside now. Okay, so this will be again the same thing. Very good. So this nothing new here. Okay, and now I am taking this transpose inside. So this will be x transpose u, very basic stuff. Then this will be 1, then 1 transpose x transpose u divided by n, and okay, so here transpose is nowhere because I have taken inside it. Okay, now I can take something common here. From this part I can take u transpose common to the left side, and from this part I can take u common to the right side. So this will be equal to 1 divided by n. So this will be u transpose. Now x minus x times 1 vector, all one vector, divided by n, then 1 transpose. This will be what? X transpose 1 vector, then 1 transpose x transpose divided by n, and then I am taking this u outside towards the right. Okay, very good. So now let me again simplify a bit. So divide 1 divided by n, u transpose, the same matrix. Okay, we will see that this is one of the very beautiful and famous matrix here. So this part, the one which I am writing just now. Okay, and now actually I can write the same matrix in now transpose form. So this is nothing but x minus, so this will be x 1 divided by n, 1 transpose. Now I am taking the transpose again. Now you see that these two matrices are the same here, right? Okay, very good. Now let us pause and see what this matrix is. So let me write this matrix separately here. Okay, so this is what? X minus x1 and then 1 transpose. Okay, so think what will be this matrix. This is our data matrix, right? Now from data matrix, remember what was the data matrix? The data matrix was this. So x was your this, right? So there were n points, x1 up to xn, right? So there were n points. So these were the vectors, So this was data matrix. Now from this data matrix, I am doing what? I am multiplying this data matrix with 1 on the right hand side. That means what? We are adding these rows. I mean, the first row, every entry of the first row is added, then second, every entry of the second row is added, and then we are dividing by n. So it seems like we are taking average of the rows. Basically, if you see the same matrix, okay, so let me write the same matrix in the row view. So this matrix is nothing but this. Remember, this matrix was what? D cross L. So there were D features of each data point, there were n points, right? So now I can also visualize the same matrix as this, FD. So there are D features. So this is first feature of every data point, this is second feature of every data point. So basically this is feature vector of first all the points, this is the second feature vector of every point, and so on. Okay, so this is same matrix. Now I am looking at this matrix in the row form or feature form. Okay, Now from this matrix we are actually subtracting what? So mean of all this. You see that we are adding every entry of this here due to this, and then we are dividing. So mean of this, okay. So basically this matrix is nothing but this. So we are, so suppose this F1 bar is the mean of F1 row vector, and F1 row vector consists of the first feature of every point. Similarly this F2 bar, okay, and so on. So this will be also a matrix here. Now every point here also, okay, so the first row of this will be F1 bar, the second row will be F2 bar, and so on. Then what we are doing, so this will be this part, right? So this will be this part. Very good. Now what? So this is basically from the data matrix we are subtracting the mean of every feature, and then we are doing the transpose of it, and that means what? This is basically the variance, in fact covariance between different feature. Every feature between any two feature, this will give you covariance, right? So basically, so like we have seen the formula of variance, right, where we were doing transpose of vector, then subtract mean square, the square was taken care by when we were multiplying the same vector with this transpose. Now we are multiplying the matrix with this transpose. That means now it will give you variance between basically different feature that we call covariance. So this matrix, so let me actually denote this matrix by S, right, or maybe sorry x tilde here. So this will be x tilde bar. So now this matrix, so basically now the variance, we can write variance of u transpose x is nothing but 1 divided by n, and then this is u transpose x tilde, then x tilde bar, and then u. Okay, very good. Now I will denote this matrix. So this matrix, and of course I will take this n below this. So let me denote this matrix x tilde bar divided by n by s. This is your famous covariance matrix. Covariance matrix. It takes it will tell actually covariance between different features. Okay, very good. So this is covariance matrix. So basically now variance is this 1 divided by n. Oh, so when n is already taken care, so I can now write u transpose s u. So we have actually simplified the variance when we project every data point, d-dimensional data point along some unit vector u. So this will be the variance where S is your covariance matrix. Now we will see what will be u such that this variance is maximum. Okay, so variance was this when we projected every data point along our unit vector u. Remember, every data point has d coordinates, so d features, so they were in the d dimensional space. Very good. And the variance was coming out to be in terms of covariance matrix. Okay, now remember here this variance is a number, right, but S is your matrix, and which is indeed d cross d matrix, because there are d features of every point. And one more thing is this, you realize this S matrix, the covariance matrix, is symmetric. Why it is symmetric? If you see that if you take transpose of this matrix, this will be in fact itself. So you just check, very simple. You try transpose this side and you will get the same matrix. Okay, very good. Now we will see that the direction along which this variance will be maximum, the u along which the variance will be maximum, is nothing but the eigenvector or a eigenvector corresponding to the largest eigenvalue of the covariance matrix S. Let us have a quick recap of eigenvectors and eigenvalues. Okay, so what are these beautiful vectors? So eigenvectors and eigenvalues. Okay, you pick any square matrix, suppose A. what will happen when you multiply this square matrix with a vector? It will give you another vector. Very simple, right? Now there are some special vector such that if you multiply them with the matrix, the output is nothing but, the y is nothing but some scaling of the same vector. If such is the vector, this vector we will call as eigenvector. So like here it will be eigenvector, this will be an eigenvector, and the corresponding scaling factor we will call eigenvalue. Very simple definition. And by the way, there is one more thing, this x has to be a non-zero vector, a non-zero vector. So at least one of the entry has to be non-zero. Okay, so non-zero vector, not all the entry has to be 0. Okay, very good. Now there are few important points related to the eigenvalues and eigenvectors. By the way, how many eigenvalues will be there? If the matrix is D cross D, so how many eigenvalues will be there? The number of eigenvalues will be D. Okay, so if matrix is D cross, if A is D cross D, this implies there will be D eigenvalues. D eigenvalues. Okay, and if you see that, suppose lambda is eigenvalue, like let me write it again, Ax is equal to lambda x, right, and lambda is some eigenvalue and x is a corresponding eigenvalue. If you multiply x with some other constant, so suppose if you replace x by Cx, basically you are scaling now further x, so this C times x, this again is satisfied, that means Cx is also an eigenvector. So there can be many eigenvectors, so many eigenvectors for the same eigenvalue, in fact infinite. Okay, and by the way, the eigenvalues will be always D, but for each eigenvalue there can be infinite eigenvectors. This comes from the definition itself. Very good. Now when the matrix is symmetric, suppose if A is symmetric, that means A equal to A transpose, many beautiful things come up. The first thing is all these eigenvalues are real, and also we can get always n orthonormal eigenvectors corresponding to these eigenvalues. What we mean by this? So first thing is the eigenvalues is this, and suppose these eigenvalues are lambda 1, lambda 2 up to lambda d. And in fact, let me arrange these eigenvalues in sorted way. So suppose lambda 1 is the largest, second largest, and so on. Okay, very good. And another beautiful factor is there can always be d eigenvectors corresponding to these eigenvalues. So V1 will be eigenvector corresponding to lambda 1, V2 will be eigenvector corresponding to lambda 2, such that these eigenvectors are orthonormal, such that V1, V2 up to Vd are orthonormal. What we mean by this? Orthonormal. The meaning of orthonormal is this: first of all these are unit vector, all these are unit eigenvectors. Okay, and second thing is, if you take dot product between any two different eigenvectors, their dot product is 0. So basically Vi transpose Vj is equal to 0 for I not equal to j. Very simple fact. This comes from basic linear algebra, and now we will make beautiful use of it. Now remember, our aim was what? Aim was this: to find u such that the variance, if you project the data along u, the variance was coming out to be this, right? So this should be maximum. So this was indeed the variance we have seen. This, so we have to find u such that this number, this quantity should be the maximum. Okay. So now as we know that S is a symmetric matrix, so S is, we know that S equal to S transpose, so S is symmetric matrix, that means there exists, and what is the order of this symmetric matrix is D cross D. So there exists D eigenvalues. So let me write these eigenvalues as lambda 1 greater or equal to lambda 2. So I am arranging these eigenvalues. Okay, very good. Okay, and the corresponding eigenvector, so let me choose same as earlier, so V1 V2 up to V2. So these are unit eigenvectors and they are orthogonal to each other. Very good. So now because they are orthogonal, right, so I can write any vector u, it does not matter what u is, as a linear combination of these vectors, right. So alpha 1 V1 plus alpha 2 V2 and so on alpha d Vd. Okay. So I can always write u as a linear combination of the eigenvectors of your symmetric matrix S, which is nothing but covariance matrix. Very good. Now I have to actually take u as a unit vector. So because the directions, only the directions matter, it does not matter how long u is. When we remember when we were projecting the point, and safely I can take u to be a unit vector. So that means u transpose u equal to 1, which you, if you will solve it as V1 and up to Vd, these are ortho normal vectors. So this will come out to be alpha 1 square plus alpha 2 square up to alpha n square. So these are the coefficient which will, the sum of their squares will be equal to 1. Now let us solve this quantity u transpose S. This is nothing but variance, right. So this is nothing but variance, and we have to maximize this, we have to find u such that it is maximum. So let us solve this. So this is nothing but u transpose S, and u actually you can write is this, right, alpha 1 V1 and so on alpha d Vd. So this will be further, so S will be multiplied with V1, which will be giving you lambda 1 V1, similarly lambda 2 V2 and so on. So this will be u transpose, this quantity will be nothing but alpha 1 lambda 1 V1, this is by the definition. Okay, and so alpha d lambda d, and so let me write here also. So this is S Vi is equal to lambda I Vi, right. So this is Vi is the eigenvector, unit eigenvector corresponding to the eigenvalue lambda I. Very good. Okay. So now let us further solve it. So if you, so again we will make use of this and we will come up with this expression. So expression will be here this. So this is nothing but lambda 1 alpha 1 square plus lambda 2 alpha 2 square. So this is just actually basic calculation, and this lambda d and then alpha d square. Now so basically the variance we can write in terms of the eigenvalues of your covariance matrix. Now as lambda 1 is the largest eigenvalue, so largest number among all these eigenvalues, right, and all these quantities are positive because these are squared. So I can safely write it as, so this quantity will be always less or equal to lambda 1 times alpha 1 square plus alpha 2 square dot alpha d square, but we know that this quantity is nothing but equals to 1. So this is equals to lambda 1. So what we get? We get this, right. So we get this, that variance which was nothing but, so when we were projecting all the data points along u, the variance was coming out to be S transpose SU, which is satisfying this. So variance will be always less or equal to the largest eigenvalue of the covariance matrix. Very neat fact. But can we get the equality? Can this maximum possible things be achieved? Can we achieve the variance as lambda 1? Fortunately yes. If you replace u by V1, a unit eigenvector corresponding to the largest eigenvalue lambda 1, so you will get the equality basically. So now the thing will be V1 transpose S V1, but you know that this is nothing but this, you can write V1 transpose lambda 1 V1. Okay, so this is nothing but lambda 1 V1 transpose V1, but this is a unit vector, that this quantity is equal to 1. So, this is equal to lambda 1. So, basically if you project our data points along V1, a unit vector corresponding to the largest eigenvalue, which is lambda 1, we will get the maximum variance. Okay. So, very good. So, our aim is achieved. So, basically, so lambda 1 is the maximum variance, possible, maximum variance, and this we will achieve when we will project all these points along the unit vector corresponding to the lambda 1. So, lambda 1 is the first principal component, we will call it first principal component, and our main goal is achieved. We will now see other principal components. Okay, so the great news is that we have found our first principal component, which is nothing but the eigenvector, the unit eigenvector corresponding to the largest eigenvalue of covariance matrix. Basically, it means that if we project our input data along this eigenvector, we will get the maximum variance, and that variance is nothing but the lambda 1, the largest eigenvalue. Okay. But what about the other principal components? What about the other directions? When we project our data along these direction, how much will be the variance? Remember, we want the second best variance, then third best variance, and also we want these principal components, the other principal components, these all principal components should be orthogonal to each other, so that we can actually represent our data points in those new directions very nicely. Okay, so let us find other principal components. Surprisingly, the other principal components or other principal directions are nothing but your other eigenvectors, V2, V3 up to Vd, and these eigenvectors are corresponding to what? Lambda 2, lambda 3 up to lambda d, and eigenvalues will again be giving you the variance along these other principal components or other principal directions, and we will prove it shortly. And we will make use of one of the powerful mathematical technique of proof. What is that? Mathematical induction. So, we will prove it using induction. So, suppose, so we will prove that the other principal components are nothing but V2, V3 up to Vd. Remember, the first one we have already found. The first one is nothing but the first one we have just now. First one, or the main one, we can say this is V1. Okay, and we will prove that these are also principal. Basically, now what we mean by other principal component? Now the second best variance will be along 2, the third best will be along V3, and the last the least variance will be along Vd, or basically these eigenvector. By the way, when I am saying the second best or third best, we have to make sure that these directions are orthogonal to each other. And by the way, we have already seen that these vectors V1, V2, V3 are already orthogonal, right? Now we will prove that these are in fact the other principal components. So let us now start our proof using induction, that V2, V3 up to Vd are the other principal components or other principal directions. Okay, so in the induction, so there is a base case, right? And base case for R is, we have just now proven that. So V1 is nothing but the first principal component, right? First principal component. Basically, along this we are getting the maximum variance, right? Principal component when we are projecting our data along this. So base case is done. Base case is done. Now the next step is my hypothesis. So I will assume that V1, V2, V1 we have already seen, so it's okay. So V2 up to Vi, so these eigenvectors are the first I principal components. So basically principal components. So this is my hypothesis. principal component. So this is hypothesis. Hypothesis. What do we mean by this? The meaning is that so V1 will give you the maximum variance, V2 will give you the second best, and Vi will give you ith best variance, and all these are orthogonal, right? We have already seen that these eigenvectors are nothing but orthogonal, right? So this is actually very basic beautiful property of symmetric matrix. Now we will prove that the I plus 1th principal component is Vi plus 1, is nothing but Vi plus 1. We will prove it, just to prove, right? To prove. If I am able to prove it, that means I will prove that all these eigenvectors are nothing but principal components. Okay, very good. So how will the proof will go on? So let us assume that U is the I plus 1th principal component. Okay, and what will be the variance along U? The variance along U will be nothing but, right, when we project our data points along U is, I mean, we have already said this is nothing but U transpose SU. I want to find U such that if I project data points along the U, the variance will be I plus 1th best, right? So we have already seen due to induction hypothesis. So I best we have already find, right? Now I plus 1th I want to find the variance, the I plus 1 best variance. Okay, so variance, very good. Now again I can write U as linear combination of eigenvectors of this matrix, right? So basically alpha 1 V1 plus alpha 2 V2 up to alpha d Vd. But by the way, because this is now I plus 1 principal component, this has to be orthogonal to the earlier principal component. So basically first I principal component, so this has to be orthogonal with them. Okay, so U is orthogonal to V1 V2 up to Vi. Okay, and so that means what? So you can actually, and U again I am taking basically unit vector. So unit vector, for simplicity, unit vector. Okay, very good, unit vector. So since U is orthogonal to this, so basically this component alpha 1 and alpha 2, these coefficients will be 0 actually. So you can actually write very simply that this is nothing but Vi plus 1 and up to lambda alpha d and Vd. Okay, and again the same thing, because we are taking unit vector, this will be equal to 1. Very good. Now let us compute this quantity U transpose SU like earlier. Okay, so you will do the same trick here. Okay, so S times, now you can write it as like U here I plus 1 Vi plus 1 plus dot alpha d Vd. Okay, and this will actually, if you solve this, you can actually take hint from above also, where we have computed the first one. So this will be nothing but so alpha I plus 1 and lambda I plus 1 alpha I plus 1 square and plus dot alpha d lambda d square. And now since, remember, our eigenvalues were what? So they were arranged like this, right? Lambda 2 lambda, so lambda 1 was greatest and so on. So there will be somewhere lambda I which will be greater than lambda I plus 1 which will be greater and equal to so on, right? So lambda d. So basically now this is lambda I plus 1, here will be lambda I plus 2 and so on lambda d. So since again lambda I plus 1 is largest among all these rest of the eigenvalues, so I can actually write it as this. Very good. And so on alpha d square, and this quantity is nothing but equal to 1. So basically this equals to lambda I plus 1. It's the same parallel thing. So basically now the best variance the I plus 1th variance is always less or equal to the I plus 1th eigenvalue. Okay, but can be achieved. So this is actually variance along U. Okay, variance along U, but can we achieve this maximum? Can we achieve? Yes, indeed. If you replace U by Vi plus 1, so this quantity will achieve lambda I plus 1. So basically, if you replace, so this quantity will be what? So Vi plus 1 transpose S Vi plus 1, and this we know that this is nothing but lambda I plus 1 times Vi plus 1. So this is nothing but Vi plus 1 transpose lambda I plus 1 Vi plus 1, and you can now write this as this. Very simple stuff. Transpose, and since this is an unit vector, so this will be equal to 1 and this will be equal to lambda I plus 1. Very good. So I plus 1, the best variance is lambda I plus 1, and when we are achieving it, we are achieving it along Vi plus 1. Okay, so Vi plus 1 is I plus 1th best direction along which if you project, if we project our data points, the data points we will get the maximum variance. In fact, this is I plus maximum variance. Okay, so this variance is nothing but I plus 1th, right? I plus 1. So let me write in bracket I plus 1, and what will be that value? Which is equals to nothing but lambda I plus 1. Okay, so using induction we have proven that V1, V2, V3 and up to Vd, these are nothing but the principal components, the principal components. So basically, so we will project our data along these new directions, new axes, in the hope of getting good variance. Okay, so and corresponding variance will be this, right? So along V1 the variance will be lambda 1, along V2 the variance will be lambda 2, and so on. Okay, dot. Okay, and by the way, along Vd the variance will be least, because lambda d is the least eigenvalue. And important thing is that, so what we are getting the new axis or new directions. Now along some direction, especially the earlier vectors here, earlier eigenvectors or earlier directions corresponding to which these eigenvalues are large, we will get maximum amount of variance, and this is very important. So we want what? Our aim was what? We want to find the directions along which, if we project our data point, the variance has to be very good, so that we can visualize this data very clearly, like Dhruv Jurel was watching these stumps. Okay, so and other directions along which the variance is low, we can actually safely ignore. So basically we have reduced the d-dimensional space into, so suppose if you remove these directions, so our directions so will be lesser than d, quite lesser than d, and we can project our data along this, we can visualize our data along this. So we can actually safely remove the directions along which the variance is very low. We can also call this as a noise, right? We are not getting any meaningful information along those directions or along those eigenvectors, so we can safely ignore this, and we can represent our data in lower dimension, lower than d. Very good. So let us now summarize it. Okay, so let us have a quick summary of what we have done. Remember, our input was what? There were n data points in d-dimensional space. That means every point has d features or d components, and our aim was what? To visualize these points. So we want to find the directions along which if we project these data points, the variance has to be very good so that we can visualize them very clearly. And we see that those directions were nothing but the eigenvectors, in fact the unit eigenvectors corresponding to our covariance matrix, and this covariance matrix was symmetric. That's why the eigenvectors was coming in very beautiful shape, that they were by default orthonormal. So we can actually represent these points in that orthonormal space. And so basically we have got d new orthonormal axis, like earlier these points were in d dimensional space. Some basically d axes were there which were orthogonal. Now we are again getting d orthogonal axis, but these orthogonal axes are now eigenvectors of our covariance matrix. But the important point here is that in these new d orthogonal eigenvectors, the first few of eigenvectors will give maximum variance possible along any directions, and we will make use of the principal components or the eigenvectors corresponding to the eigenvalues having good amount of variance or good amount of magnitude. Rest of the eigenvectors or rest of the principal components we can safely ignore, because these will have less variance, they will capture the noise, so we can safely ignore them. So in summary, we are getting very nice eigenvectors, in fact the principal components along which we can project our data so that we can see the data very clearly. And usually the number of such useful principal components is way lesser than the number d, the d dimension where we were projecting earlier. With this, I am stopping this lecture. I hope you have enjoyed it. I will put some more links related to the eigenvalues, eigenvector, especially those of symmetric matrix, in our description. Thank you very much.